Hi, welcome to Ushendra's engineering tutorials. Yet another important video from the playlist control systems. It's designing a PID controller. Design uh, PID controller. Guys, if this is the very first video, if you're watching mine, go through the previous video. I'll be providing the link in the description box. I have derived all the expressions for these constants Kp. How did we get cos theta by A1, Kd in this expression, and this one, what is this product, and Ki, and how to evaluate the value of theta. I have done a separate video, like an introduction you can say. So without going to that, without going through that video, it will be quite confusing if you straight away start with this one. Why, how this theta, how to evaluate A1, and what's omega. Okay, omega 1, that will be obtained from the given question, but how to evaluate all these expressions, please go to the video. You can find in the description box. I have given in detail. Okay, now as far as this problem is concerned, it's asked to design a PID controller, right? PID controller, and open loop transfer function g of s is given as g of s. It's let's say, not let's say, it's given as 100 upon s plus 1 into s plus 2 into s plus 10. Okay, so this is the given open loop transfer function, and for this one it's given as a the desired, like a phase margin is desired to be 45 degree at 4 radians per second, right? And also a requirement is the steady state error should be equal to 0.1. The design should be in such a way that the steady state error for the compensator system should be 0.1 for a ramp input. For ramp input. Okay, these are the given information in the given question. The open loop transfer function is given this one at omega equal to 4 radians per second. The desired phase margin is 45 degrees, and the steady state error should be 0.1 for a ramp input. This is given. Okay, so guys, from the given question itself, something has to be extracted. Now this at 4 radians per second is given. Okay, now this one will be our omega 1, that will be omega 1. Okay, so omega 1 from the given question, omega 1 will be equal to 4 radians per second. Okay, so as soon as we have omega, we can evaluate the value of A1. Yeah, we can evaluate the value of A1. So what is the value of A1? The magnitude A1 is the magnitude of the open loop transfer function A plugging in omega equal to omega 1, right? So what is the expression for the magnitude of g of s, the open loop transfer function? G of s will be equal to, it's guys, the magnitude. Writing for the magnitude, 100 will be 100 as it is. Okay, so how to write the expression for magnitude? If you have a plus jb, the magnitude will be under root a square plus b square, isn't it? So in that case, imaginary is absent over here, right? So this will be 0, a square under root a square, 100 square under root, so that will be simply 100. And what about this one? This is a and this is b. So sorry, I forgot to mention something. Subjecting s is equal to j omega 1. Okay, so g so guys, g of j omega 1, plugging in s is equal to j omega, straight away j omega 1, which is equal to this one, which is given in the question itself. So what is that? J omega 1, s is equal to j omega 1, 100 as it is in the numerator. So s is equal to j omega 1, so that gives us under root 1 plus omega 1 square into under root, for this term it's 4 plus omega 1 square. Now this one will be j omega a plus jb, right? So into under root, now this one will be 100 plus omega 1 square, right? So guys, this is the equation for which gives us a1, which gives us a1. So plugging in the value of omega 1 is equal to 4 radians per second. So a1 will be equal to 100 by under root this one. This will be 17. Omega 1 is equal to 4, isn't it? 4 square, that will be 16 plus 1, that will be 17, into this one will be 16 plus 4, that will be 20, into this one will be 100 plus 16, so 116 over here, and this should be, if I am not wrong, it should be 0.5. Guys, 100 by under root this one, yeah, it's a 0.5. Okay, so guys, this gives us the value for a1, which we have to plug in for this one over here. We need to have that one, right? Even evaluating for kd, we need a1 to be plugged over here. So guys, this gives us a1. So how to evaluate for theta? We need theta, isn't it? We need theta from here and here. We need to plug in theta over these expressions. For kp we need to plug in, and kd we need to plug in, right? So that gives us, we need to go for the phase angle expression for this one angle. So to evaluate the phase margin of the uncompensated system at omega equal to omega 1, angle g of j omega 1 of the open loop transfer function, it's guys, this one will be 0, and for this one what we have is over here, okay, minus tan inverse, it's a j omega plus 1, isn't it? A plus jb, that will be simply omega 1, substituting s is equal to j omega 1, minus of this one, it's a tan inverse omega 1 by 2, okay, and going ahead with this one, it's a minus tan inverse, how much it is? Omega 1 by 10. So guys, plugging in the values of omega 1 equal to 4 radians per second. This is the desired the specification. We have to design a PID controller for at this frequency, so that will be considered as omega 1. Okay, so in that case what we have is minus tan inverse 4, omega 1 is plugged in with 4, minus tan inverse 2, 4 by 2, minus tan inverse 4 by 10. So evaluating this value, what do we have? As let's try for that one. Minus of tan inverse, this is only for phase angle phi, okay, phi at omega 1. So tan inverse 4 minus tan inverse 2 minus tan inverse what is that, 4 divided by 10 gives us, guys, it's a minus 161 point, yeah, 2, we don't need that. Why? Because it's not beyond 0.5. I mean 161.6 something else, we would have gone for the next level. It's simply minus 161 degree. Okay, this is for the value of phi at omega equal to omega 1. And now from here the phase margin could be calculated for the uncompensated system, and that will be this one. Okay, so here what do we have? Phase margin is defined as 180 plus resultant phase at the desired frequency, isn't it? So here that will be 180 degree plus the resultant of this one, in the sense minus 161 degree. The expression for phase margin, the relation for a phase margin. So 180 plus answer gives us the desired, I mean, yeah, it's a 19 degree, 18.799, that could be rounded to 19 degrees, guys. Okay, so this will be, now this will be our, yeah, this uncompensated phase margin of the uncompensated system, from which we can calculate the value of theta. making use of this expression. So desired is this much, which is asked in the question itself. Okay, desired is 45 degrees, and so from this one, making use of that one, we can evaluate the value of theta. Theta from here, theta will be equal to desired phase margin minus the phase margin of the uncompensated system. Desired phase margin is this one, this much, 45 degrees. 45 degrees minus just now we obtained the phase margin of the uncompensated system at omega equal to 4 radians per second to be 19 degrees. So 19 degrees. So which gives us 45 minus 19. Yeah guys, it's 26 degrees. Theta will be equal to 26 degrees. Okay, so this is the value for theta, making use of this one, plugging in the value of theta over here and over here later on. So how to obtain the value of ki? Guys, here not making of this expression, but we have to stick to this one. From here, from this very given specification, we can evaluate the value of ki. So how is that done? Guys, I need this place input, and we have to go for the steady state error. Even that link I have done a video on steady state errors. Go to that and I'll provide the link in the description box. Okay, so guys, steady state error ESS for a ramp input, ESS for a ramp input, it's given as 1 by kV. You have to have this from the previous knowledge of steady state errors, kV, and it's given steady state error ESS is equal to this one, 0.1 to be for the design purpose. I mean, the design should be in such a way that steady state error is 0.1 for ramp input. Okay, so ESS, plugging in the value of ESS, it will be 1 by kV is equal to 0.1, which implies kV equal to 10. Okay, so from this relationship, from these expressions, kV will be equal to 10. Now what is the expression for kV for a ramp input? kV is given as limit s tends to 0 s into, guys, now hold on, and what value comes over here? This should be met after providing the compensation, not simply for the open loop transfer function without compensation, but this steady state error is to be satisfied after the compensation is provided. So after how the compensation is provided? By multiplying the G of S with the GC of S. That's the complete compensated system. So what we have is GC of S over here, GC of S into G of S. Okay, G of S, and plugging in those values. So kV, it's from here, it's a 10, which is equal to limit s tends to 0, s from the previous simplification for kV. Now GC of S is this much. What is that? This one, this expression into, it's a S kP plus ki plus s square into kd whole by s into G of S. We need to plug in this one also. That's 100 by much s plus 1 s plus 2 into s plus 10. Okay, so guys, careful watch over here, this s, and it's a multiplication, so this s gets cancelled. Okay, right, we have to plug in s is equal to 0 according to the definition for kV, according to the equations derived for steady state error and kV. We have to plug in s is equal to 0, so we don't have this anymore, right? And plugging in 0, this becomes 0 because it's associated with s. This becomes 0, even this becomes 0, right? So what we have finally left is 10, which is equal to kV from the previous given data, which is equal to 100 by, guys, even this becomes 0, so we are left with 1 into this becomes 0, so that we are left with 2 into this becomes 0, so that we are left with into 10, right guys? So this will give us into ki, we have this one, it's a multiplication over here into ki. So how could I forget that? Ki, right? So with this knowledge, what do we have? It's a what's that? Ki will be equal to, it's 0 gets cancelled over here, it's 5 times, right? 5 times, and ki will be equal to 10 by 5, which is equal to 2, which is the value for ki. Okay, this is the value for ki equal to 2. So that to have a steady state error of 0.1 for the compensated system for a ramp input. Okay, so make a note please guys. The design is for PID controller, PID controller, and in that process we need the values of A1, theta, and ki is equal to 2. Ki is found out to be 2 to meet the steady state error from the knowledge of meeting the steady state error requirement. That's the procedure to evaluate PID controller. First we have to evaluate the value of ki, integral constant, making use of the given data, and in such a way that it meets the specification value of steady state error. It will be specified. This is the procedure always for evaluating PID controller, right? If in the case of PD controller, guys, in case of PD controller we will be in need of Kp and Kd. We will be in need of Kp and Kd for a PD controller. Ki is assumed to be 0, and this theta A1 value and theta value is enough to evaluate the values of Kp and Kd. Then we can go ahead with the design PD controller. Even with a KPI controller, we can make use of theta A1 and theta to evaluate Kp and Ki from this, making use of these expressions. Okay, right? Not in this way, but this procedure is valid for designing a PID controller. The expert suggests, right? In that process, in that case, Kp can be evaluated to be, Ki is 2. Okay, Kp, the value for Kp is equal to cos theta is 26 from here, 26 by A1 value is 0.5, which is equal to, guys, it's a 1.79, so 1.8 Kp, right? And value for Kd can be evaluated making use of this very expression, this one here, this one. So Ki found out to be 2 to meet the steady state error requirements for the compensated system. Okay, so omega 1 square is a 16, isn't it? Why? Because omega 1 is 4 from the given data, for the given data, and sine theta it's 26 degree sine theta from here, this value, and A1 it's a 0.5 again into 4. So how much is this? So guys, it's 2 divided by 16 plus sine 26 by 0.5 into 4. Hey guys, that's 0.341, just leave it, 0.344. That's the value for Kd, right? And we have Kp, Ki and Kd. That's enough for a PID design. So Gc of S, which provides the compensation. Remember from the previous expressions we had S times a bigger one, S times Kp plus Ki plus S square Kd. Hope you remember this expression from the when I was trying to derive all these expressions, we came across this one into by S. Okay, so plugging in the values of Kp, Ki and Kd from this one, Ki is to be 0, Kp is 1.8 and Kd is 0.344. Okay, so what we have is S in the denominator as it is, no change in that. S times Kp, how much it is? 1.8 plus Ki, it's a 2 plus KD S square times KD, right? S square and KD 0.344, which we have evaluated, right? So more precisely, in a very standard form, getting that to a standard form, it's a GC of S compensator. Okay, S as it is 0.344 as common from all the terms, S square plus 1.8 by 0.344 into S plus it's a 2 by 0.344. Okay, so guys, this is the one. Simplifying this even more, so what do we have is 0.344 by S into S square plus, so how much it is? It's 1.8 divided by 0.344, isn't it? So that is yeah, 5.23 S plus it's 2 divided by this one, it's a 5.8. Guys, this is the transfer function of the PID controller which we are in search of, right? So this is GC of S. Now what will be the final transfer function? I mean the compensated one. It will be like this one. So guys, it should be PID controller. We have in a block diagram representation, we have what is that? The GC of S comes over here, right? What it is? 0.9. After introducing this will be GC of S, and we'll be having that open loop transfer function over here, G of S with a feedback, with a unity feedback. Yeah guys, this one, right? Now GC of S is this one, and G of S is the given open loop transfer function. Make a note please. This is the given open loop transfer function. This was given in the question, and this is the time constant form, taking out 2 common from here, taking out 10 common from here, and simplifying. This is the time constant form. Okay, the analysis is in frequency domain, so definitely we have to convert that to time constant form for some important simplifications. Okay, we can go ahead with this one, but still this will be more convenient, taking out common and getting it ready. Okay, on the other hand, now this is the transfer function of the compensator with all the requirements here, like taking out 0.344 as common from this one. I need the please. Okay, so 0.344 taking out as common from here, in the sense bringing this equation to a standard equation, S square plus 2 zeta omega n into S plus omega n square, this standard second order system, right? So this is the transfer function. Now what is the final conclusion? Here we need to have this one. The final transfer function will be like this one. The compensator comes over here with a 0.344 into S square plus 5.23 S plus 5.8, a bigger one please, it won't be visible properly, 5.8, close the bracket, by S. Guys, this will be the compensator which has to be introduced to meet the following specification. Okay, the required specification, and the open loop transfer function comes as it is. What's that? Phi by, from here, 1 plus S into 1 plus 0.5 S into 1 plus 0.1 S. Okay, so now this is the complete conclusion. You have to show this. This is the given open loop transfer function. By introducing the PID controller, that phase margin will be met. and we have to prove that did we really meet the desired specification, the values of ki kp. Is that okay to obtain the required phase margin? Now we have to write the expression for the phase margin after multiplying this one. It's a guys guys remember this one, please. Going back to the basics of the board plot, I cannot explain now, but this is second order system. It's a second order system, and for the second order system we have to evaluate, comparing this expression with the second order system, we have to evaluate the value of the corner frequency. Yeah, it is required. We have to evaluate for n, so that will be, guys, this is very much similar to the second order system. A square plus 2 zeta omega n into s plus omega n square. Now omega n square will be this one, omega n square will be equal to 5.8. so from this one omega n will be equal to, that gives us under root 5.8, which is equal to, guys, it's 2.4. omega n is 2.4. so why this one? From the exercise done on board plot, you might have been informed that we need a correction in the expression for the phase angle. If the value of omega plugged in the equation is greater than, we have different values, right? If the omega value is less than omega n, we don't need a correction. When this omega value to be plugged in the equation is greater than omega n, we need a correction to be done for the second order system, which you will be having some inputs when you were doing board plot or in the frequency domain, in polar plot, etc., Nyquist plot, right? According to that one, guys, this doesn't contribute any phase angle, okay? The phase angle of this entire system. Now this 1.72 doesn't contribute any phase angle. Why? Because it's a 0.9. What was that value? 0.344 into 5, that's 1.72 plus j0. We don't have that imaginary, and theta will be equal to tan inverse imaginary 0 by 1 point, and that leads to 0. So the constant doesn't influence the phase angle. So straight away, now this one, yes, this one, right? For this one we need a correction. Why? Because we have to plug in the value of omega, which is equal to 4, which is equal to omega 1 as far as this problem is concerned, which is greater than the corner frequency of this function of the second order system. So guys, I cannot give you much explanation. Why? Because it's going very lengthy. So please go to that one, board plot, for writing the expression for the phase angle when the equation contains a second order system. And we have two conditions. One is that value, plugged in value, less than omega n, we don't need any correction. If the plugged in value of omega is greater than its corner frequency omega n, we need a small correction. That small correction isn't a big rocket science, adding 180 degree. So especially for this one, this doesn't contribute any phase angle. The phase angle expression for this one is 180 correction, okay? 180 plus tan inverse. It's in the numerator, so no negative, it's plus tan inverse. Guys, imaginary by real, right? A plus b by a, isn't it? So this one will be b. 5 we have, sorry, b by a, tan inverse b by a, in the sense where is left over with this will be the imaginary. This goes away, we don't have this imaginary again. Why? Because s is equal to j omega, so j becomes minus 1, we don't have imaginary over here. Now this will be the imaginary. 5.23 into omega is here, so into 4 by the real part, 5.8 minus, and it will be omega 1 square, isn't it? Plugging in s is equal to j omega, plugging in that will be, we will be left with square, so we will have to plug in 4 square, that's 16. Okay, so this is from this term. We have no phase, this value doesn't contribute anything for the phase value. Now this one, it's in the denominator, that gives us minus, continuation to this one, okay, minus 90 degrees, right? So guys, you are not new to this one. I don't need to explain much about how this is minus 90 degrees, okay? So no. And this is for this one, okay? So for this one, again it's in the denominator, so it's minus tan inverse omega, so straight away for that value of omega which we have designed for, minus for this one tan inverse 0.5 into 4 for this one by 1, that's it. So now this is a simplification while we write for converting this to time constant form, while we write the expression for phase angle. We are ready straight away, right? That doesn't give a much complexity. This is for this one, and the tan inverse 0.1 into 4 for this one, okay? This is in the numerator, so it's positive, and this is for the correction, okay? This is for the correction, 180 plus tan inverse for the second order system correction, minus, it's in the denominator, so minus 90, right? And for this one, this 1, 2 and 3. Guys, we have plugged in omega equal to omega 1 equal to 4 radians per second. Let's check. So guys, finding the phase angle, phase angle, this one, phase angle at omega equal to omega 1, which is equal to 4 radians per second. This value is minus 135 degrees, right? And how to, what is the value of, how to obtain phase margin? Phase margin is defined to be 180 plus the resultant at omega 1, isn't it? So that will be 180 minus 135, which is equal to how much? 180 minus 135, guys, it's 45 degrees, okay? 45 degrees, which is the required phase margin. Previously the phase margin was 20 something, I don't remember because done back, but that didn't meet the requirement. The desired phase margin was to be 45 degrees here, 45 degrees. So this value of the PID controller is perfect. The design is perfect. Now this is the conclusion. You have to prove this one, and it was proved, right? AC into A1 equal to 1. Now this, even this gives, it's correct. Even this gives even more cross check that it's correct. The design is perfect. So guys, hope you understood the analysis. So I don't ask you for any subscription, but please, if you find the video worthwhile, give a thumbs up, please. Thanks for watching.